Okay, 8:15. Welcome back to our plasma physics lecture for energy engineers and friends. We reconvene after almost a month since our last lecture, and we changed topic. We start today a long topic about waves in plasma. So today is going to be the 26th of April, and the main argument or topic of the day will be waves. So we start with waves. And general properties of waves, and then we move to waves in a plasma. And as always, we start from what we know already about, for instance, waves in gases media, like waves in air, which are acoustic waves, the one that allows us to produce sound and hear each other and communicate. So the starting point is the wave equation in 1D. So the, let's say, wave equation in 1D, I mean in one spatial dimension. And then we expand this into a 3D formalism later on. So what is the wave D? A wave equation is a differential equation of the second order.
Prof, la registrazione.
Excuse me?
La registrazione.
Sì.
Cioè non registra la lezione.
Sì, è registrata. Vede che c'è scritto in live. Non le risulta?
Ah, sì. Ok, scusi.
Okay. So the equation is second derivative with respect to time minus v squared, which is going to be the characteristic speed of the wave, times the second derivative with respect to space. In 1D is x, and this is a differential operator, which in 3D becomes the D'Alembertian operator. And this is applied to a function of f, generic function of the position x and time t. So the two variables that the wave is mixing is, one is the spatial coordinate x, and the second one is the time derivative. And the solution to this homogeneous equation is called a wave solution. So this is the structure of the wave operator, differential operator, applied to a generic function. We have to seek for a solution of the homogeneous equation. So another way to write the same equation in an abridged, in a short format, without writing so many partial derivatives, is that we are going to use in our course. Maybe you found already with Professor Azzeni for the MHD equations, is to just find an abridged version of the notation. So the same equation, we can write it as second derivative with respect to time, and we put it down here, the index, minus v squared, second derivative with respect to x, applied to f, the function, the test function f of x and t equals to 0. Have you encountered already this notation before? Yes, no, who knows? Maybe. Don't hear any answer. Avete già visto questa notazione?
Non mi sembra.
Ok. Allora la ripetiamo, la ripeto in italiano per essere più chiaro. La derivata parziale rispetto al tempo la sostituiamo con la derivata parziale rispetto a t, la derivata parziale rispetto a x diventa la derivata rispetto a x, e ad esempio se abbiamo la derivata parziale seconda rispetto al tempo e rispetto a x, questa diventa t e x, e la derivata seconda, derivata seconda rispetto a x due volte diventa derivata seconda rispetto a x. Questo è un modo per abbreviare la notazione, per non scrivere ogni volta le frazioni. Allora, so let's go back to English, and this differential operator here is the wave operator. We can factorize it into two other differential operators. So we can write this as time derivative minus or plus v derivative with respect to x, which multiplies the time derivative minus v derivative with respect to x applied to the same function. Okay, so our differential operator can be written in this way because the derivative with respect to time and respect to space are commutating. So we can exchange them, and actually it's possible to write the second order differential operator as the product of two first order operators, and each one of the two correspond to a different solution, which we'll see in a second. The first one is called the progressive wave, and the second one is called the regressive wave. Progressive means that the wave solution is moving in the direction of x, whereas the other one is describing a wave which is moving in the opposite direction, so along minus x, where x is the direction of the spatial direction. So we can actually seek a solution of this operator, and we call, for instance, that f plus, well, let's use this notation, f plus is going to be a function, a generic function of space and time, which has just this important combination of space and time. So this is just, we call it f plus. It's going to be the progressive direction, and as this dependence, so this x minus vt. Okay, and it's called the progressive wave. The other solution to the other operator, f minus, is the regressive wave, is any function of as any one-dimensional function which has an argument as an argument this difference x, in this case is a sum, x plus vt. So for any solution f which is a 1D function whose argument is written as x minus vt or x plus vt, we have in one case the progressive wave, in the other one the regressive wave. So it means that we can write our solution. For instance, we take the differential operator for the progressive and regressive wave. So we apply dt plus minus v dx applied to a generic solution. We invert this, the regressive or progressive wave of x and t equals 0. It means that, for instance, the regressive wave, the one with plus, is solution for the differential operator dt minus v dx. Whereas the progressive wave, let's say the regressive wave, for instance, the one with minus, is a solution of this differential operator. Okay, the equation is linear, so we can use the superposition principle. So we can construct a general solution to the wave operator as the superposition of individual solution of the regressive wave, so the regressive part, and of the progressive part. So let's take our equation here. So let's call it equation 1. And we say that equation 1, which is the wave equation in 1D, is a linear equation. So it's a linear operator. Therefore, we can use the superposition principle. Il principio di sovrapposizione delle onde. Which means that a general solution to our wave equation, so a general wave, can be constructed as the sum of a progressive part, so f plus, which is x minus vt, plus a regressive part, f minus x plus vt, with appropriate coefficient. For instance, we put here an a and the c and the b constant in front. Whatever a and b and whatever f plus and f minus is a solution to the original wave equation. So to understand what is, for instance, the progressive wave, let's focus our attention on just the progressive part, and let's draw this cartoon here. So we have, for instance, that our space is x, and at time equals 0, we have a wave profile, so we call it f, and we have a wave profile that goes like this, more or less. Wait a second before writing this diagram in order to understand it. So we call this, at time equals 0, the wave profile, or the waveform. So t equals 0. So we call it f at t equals 0 as a function of x. As time increases, so as time goes from 0 to a generic time coordinate t, what is happening to our function? So let's take it and copy it to the right. Exactly the same frame of reference. What is happening is that the whole solution form is rigidly moving to the right. So this is called a rigid advection of the whole wave. And what is the distance? For instance, let's take a peak, the peak of of the wave as a reference. For instance, suppose the peak at time t equals 0 was at the origin of the x coordinate. So let's put the origin here, 0, 0, 0. So if we look for the distance traveled by the peak, then the distance traveled by the peak in time t is this distance here. And this distance is just v times t, where v is the characteristic velocity of the function. So now we see that in our progressive wave, and the fact that the argument of the function is coming in the form of x minus vt, okay, it means that any initial value of the function of the wave solution is rigidly advected towards the right, and the v is actually the speed at which the whole wave is moving to from left to right. And as you see, applying a dimensional argument to this difference here. Here we have a length, here we have time, and obviously that's the reason why we call this parameter here in front of time as the velocity, in order to have actually the difference between two lengths. So what I draw at in the second plot here is actually the profile of our solution, the wave solution of function of x at time t. And this abridged version of notation is just our solution as a function of x at time 0, so at the initial time. So this is what is happening, and this is true for any waveform or whatever form, as long as the function f is a 1D function of not just x and t as independent argument in the function, but the position x and time t are entering the function f of the wave in this particular form. This is enough to assure that any profile is a solution of a 1D equation. So here, as you can see, we are not talking about any particular solution like cosine and sine function or whatever oscillating function. Whatever profile you imagine is a solution of a 1D equation. Okay, so our generic solution is, as we wrote it before, is a function f of x and t, which is just in the form of x minus vt. And this is I'll write it again, is the progressive solution. If you change a plus here for the minus, then it means that basically what is changing is the sign of the speed, and the speed is moving in the opposite direction. So if you put a plus here, it means that actually the profile is moving with respect to time in the opposite direction. Let's leave it where it was. Okay, so having a general function f as a function of this argument here, x minus vt, we can go from the x space into its Fourier transform space. So we go from space x and time t into the dual space of the frequencies, where we have the spatial frequency or called the wave number k, and we go for space, and for time we go into the frequency domain, which is the angular frequency of omega of the wave. Let's see how we move from x and t into k and omega space. So to move, we have to use the, into this space, we have to use the Fourier transform. So we can, if you remember, any function of x and t in 1D, and in our case is, for instance, let's take the solution at x minus vt. So our solution at time equals 0. Actually, we can take out this time t here as the Fourier transform of what? So we move on to the Fourier transform. We can write f as 1 over square roots of 2 pi, which is the normalization factor in 1D for a Fourier transform. And then we have the integral from minus infinity to plus infinity in k space. This is the Fourier transform in what is called the physicist's notation. So we have the amplitude of f in Fourier space, which is f of k, where k is the wave number, times an exponential factor, which is called I, k, which multiplies x minus vt. So our argument in the original space is multiplied by the ik factor, and then we integrate over all the k numbers. Okay, this is the Fourier transform. And let's arrange a bit the notation. So we have the normalization factor, 1 over square root of 2 pi in front. Then we have, pay attention to distinguish between f, the function in the configuration of x and t, and that in space, and that one in the Fourier transform space. We are going to use a hat in order to understand that this is the Fourier transform function in k space. So from now on, I'll drop the domain. So it's going to be just an integral over all k space from minus infinity to plus infinity. And we have the f hat of k. And then we rearrange the exponential. So we have one factor, which is e to the I imaginary unit times k times x. And then we factor the other term as minus I kvt. And at this stage, we define a new quantity, which is called omega. So we take the Fourier transform with respect to the first argument, and now we introduce the omega quantity, which is just defined by saying that omega is v times t. V times k. So that here in front of time, we want to have an angular frequency. So as we have when we do that Fourier transform with respect to time instead to respect to space. And if we define omega in this way, we can rewrite our Fourier transform as the normalization factor, integral of the Fourier transform function as a function of k times e, and the exponential now becomes as I that multiplies open square kx minus omega t integrated over the dk. Let me check. So we take a break around 9, so we make 3/4 slots lectures, and then we take a small break. Okay. And what we see here, that now in Fourier transform space, we exchange x minus vt into the same again, a difference between two terms. One is depending on k and is going to be the connected to the space frequency in Fourier transform space, and the other one which is connected to omega and to time. Okay, so this is important to remember that a generic wave in 1D can be thought as the superposition, because, okay, here again, we have in action the superposition principle. Any of these f hat k is what is called a different component of the wave. As we'll see that in 3D it's becoming a plane wave, and we have a superposition of these waves. These are the amplitudes of the wave in k space, and we have the oscillating term oscillating in space and time. So you know, and then we are summing up all these terms. So by this is possible because the operator is linear, so we are applying the superposition principle. Okay, we change the notation in order to arrive to this exponential factor here, and we define now a new quantity we are going to use in plasma physics. All this effort was to achieve this notation, where we can now say that we define what is called the dispersion relation. Dispersion relation is a function that describes how omega and k are linked together in order for the solution for this exponent here to represent actually a solution to the wave equation. As we'll see, so this relation is a function that links omega as a function of k, or k as a function of omega. And in our case, we say that omega as a function of k is just the definition that we used above. So a very simple dispersion relation. So this relation is telling us that for any k number, which is the corresponding omega angular frequency of the wave that satisfies the wave equation, okay, for any k, we multiply k times v, which is the speed of the wave, and we get the corresponding angular frequency of the wave. So remember that v now is the speed of the wave. Very often, instead of this notation here, we'll use the square of omega, and you'll find that the dispersion relation will be written as, for instance, as omega squared as a function of k is v squared k squared. So usually in plasma physics, it's very common to use, instead of the linear expression, to write the dispersion relation as an equation that involves the square of the angular frequency and the square of the wave number, k. So let's see what this dispersion relation corresponds to. So we go onto Fourier transform space from x and t. We go into omega and k vector space. And we have, for instance, it's usual to draw the dispersion relation into a plane where we have on the horizontal axis the k number, the wave number k, and on the vertical axis the angular frequency. So let's give the proper name. So omega is the angular frequency of the wave, and k is the wave number. Which are, as you should know, are linked to, for instance, the frequency of the wave. So 2 pi nu, where nu is the frequency, is omega, and the wavelength is of the wave is 2 pi over k, where here we have the actual frequency in hertz, and lambda is the wavelength. So the distance between two peaks or two valleys of the wave. Okay, so we have our Fourier transform space here, and let's remember that our dispersion relation is omega equals v times k in this case, and we can write it as the progressive part when v is positive. We have that for each k that we can take here, the corresponding omega is equal to, let's write it here, vk. Is a line, it's a straight line with originating from k equals 0. So for k equals 0, omega is equal to 0. And this is representing the progressive wave. The other solution is the regressive wave, so which is with the color code I used before, I'm drawing in red. So for instance, if we take this k vector here, which is negative, we go to this point here. Okay. And this part is telling us that omega is equal to minus vk. So what is the dispersion relation telling us? It's telling us that in all in this plane, not all values of omega are solution to the wave equation, but only one. For every k is a single value function, as you can see. For any k, the corresponding omega is vk on one side. If k is negative, is minus and minus k on the other side. You see that the k vector is changing in sign. We can have a k vector positive, which means that actually the speed of the wave is going to be positive when the wave is a progressive wave. And we can have a negative k vector telling us that actually that solution in the superposition is corresponding to a regressive part of the wave. So a generic wave moving in 1D and being a solution to the wave equation is the superposition of many progressive waves with different amplitudes and many regressive waves with their own complex amplitude. And another thing that we have to remember is that the Fourier transform is operator in complex space. So when we have here, we have actually a complex valued amplitude, and we'll see that, as you know, the modulus of f hat is the actual amplitude of the wave, and it's called the azimuthal angle in the complex plane is telling us which is the phase of the wave. And the different components of the wave can have different amplitudes and different phase relative to each other. So what we have to focus now is on the role of the phase. So what is the phase? Actually, is let's focus our attention on the exponential term. So the e to the I kx minus omega t. This is the exponential factor, which we can call it as e to the I phi. The phi is the phase of represented by this term. And so the phase of the wave, phi, is a function of x and t, which is just kx minus omega t. There's a simple relation between the two. And the phase is, you see, if we freeze time, so this is constant, for instance, at a certain point, the phase is increasing as a function of x with a k vector. So it's telling us how the phase is increasing in space. On the other side, if, for instance, we freeze x, so we look at a given point in space and let the time to evolve, then we see the phase is changing, and the rate of change of the phase in a given point is minus omega. So one is progressing, the other one is regressive, and we want to see a given phase, how this is moving in time. And if we lock on a given phase value, we want to see what is the speed of changing of the phase. So if we go and say, for instance, we want to see the differential of the phase, and we want to see want to sit on the same value of the phase on the wave. So we phase lock and we seek for the differential solution to what? If we differentiate this relation here, we find that actually we have k dx minus omega dt. So we differentiate in the original space, so space and time, not in the Fourier transform space, and we impose this to be 0. So we look for same speed or constant speed points. How these points are related, we see that we can have on one side, we put all the differentials, dx over dt becomes omega over k. And this is actually the definition. You see, this is a velocity, and this velocity is called the phase velocity. And we call it v phase. So this is actually the speed at which constant phase argument is moving in x and t. So this is very important. And now this is the definition of the phase velocity, the other definition. So let me recall it here. Phase velocity is defined by omega over k. And now we have the definition of the group velocity. Did you find already in your course the group velocity, la velocità di gruppo? L'avete già vista?
E l'avevamo vista in Modern Physics.
Okay, so the other term is the group velocity. We call it v group, and is defined by what? If you might remember for other courses, is the definition is d omega over dk. So what is important to remember from other courses? The phase velocity is the mathematical speed. Can be very large, can go to infinity. But we are talking about waves, and waves are transporting observable quantities like momentum, like energy, so like pressure. And obviously in physics, we don't have that any quantity can be transported from one point to the other one at a speed larger than light. So we have a maximum limit in speed, which is the speed of light. So it's important to remember that the phase velocity can become superluminal very easily, can go to infinity. We'll see many examples where the phase velocity goes to infinity, but that is just a mathematical velocity of the phase. And we'll see that this is not connected to any transport or any physical quantity that can be observed. So I call it somehow, in order to remember this is a mathematical speed and can go to infinity. On the opposite, we have what is called the physical speed. Which is the group velocity, which is nothing else than the derivative of the omega of the angular frequency as a function of k, and is called the group velocity. So it's looking at this the velocity at which a certain waves component are moving along the wave packet, and this is related actually to the transport of physical quantities. So this always has to be always. So let's put it can go to infinity. It has to be always less than, smaller than c of the speed of light. And as you can see here, what is the omega dk meaning now? We can link to the definition of the dispersion relation. Remember that we have omega as a function of k. this is our dispersion relation. In our very simple case is, and let's not write it at the moment, it's just the dispersion relation. So the group velocity is nothing else than the derivative of omega k of the dispersion relation as a function of k. So here now you see that, okay, well, it could be interesting to change the color scheme to this. So here we have three ingredients here: the group velocity, this, okay, time to have a break, nice time. So we have the phase velocity, the group velocity, and the dispersion relation. And all these three quantities are related. So we have, now that we introduced the 1D wave equation, we moved on to Fourier transform space. And so we have that we exchange X for K, and we change time for omega. And then the ratio of these two, omega and k, which are function of, which are solution of the wave equation, is called the phase velocity. And then we go and look for a relation that tells us which is the function that links for any k the corresponding omega, in order for omega and k to represent the solution to the wave equation. And this is called the dispersion relation. So now when we have omega as a function of k, we can take the derivative of the dispersion relation with respect to k, and what we get is actually the group velocity. And this group velocity will represent the speed at which physical quantities like energy, like momentum, and so on, are transported by the wave. Okay, let's take a break here. We'll see in again in 10 minutes time, and we discuss a little bit more about the dispersive and non-dispersive media. Are there any questions? Okay, we'll take over from here in 10 minutes time. Okay, welcome back. Can you hear me and see the tablet again?
Sì.
Okay. So we introduced the concept of dispersion relation, and we applied to a case where the dispersion relation is omega equal v times k. And actually, what we see here is what is called a non-dispersive relation. And then we'll try to understand this, because the simplest example that we can start with is actually an example where the dispersion relation is describing a non-dispersive medium. What does it mean, a non-dispersive medium? It means that, and we'll find in a second, that the concept of dispersion is the fact that the speed, the phase speed, the space velocity, is related to the group velocity. When the two are the same, so when the phase velocity equals to the group velocity, then any component of the wave in the Fourier space is moving at the same speed. And therefore, the relative phase between any component of the wave is not changing in time. And if the phase is not changing in time, the wave packet, so the waveform, is not distorted as a function of time. All the components are moving in the same speed, and they are advancing at the phase velocity. And this is not only the phase speed, but the group speed. So it's not changing locally. And therefore, the wave packet is moving rigidly and is not distorted. So there's no distortion of the wave, and then we say there's no dispersion of the phase. So this is the reason why we're using this name, this particular name, dispersion relation. So in our case, let's see what is the group velocity and what is the phase velocity. So let's change. If omega k equals vk, then the phase velocity, v phase, is just defined by the ratio of omega over k for omega and k, which solution of the wave. And let's compute the group velocity. V group is equal d omega over dk. So is the derivative with respect to k of what? Of v times k. Vk, which is equal to v. And if you do the same here, you see that omega is just v times k divided by k. And we recover the fact that in this very simple case, the phase velocity is v and the group velocity is v. So we somehow find already that the group velocity was v because the whole wave packet or waveform was moving at constant speed v at the beginning. And what we found here is actually the v is the speed at which the phase is changing in time as well. So in this case, we say that this is a non-dispersive medium. When v phase equals v group, then the medium is non-dispersive. What's the medium? It's the environment in which the wave is moving. For instance, the acoustic speed is moving in air. So the medium which is supporting the wave phenomenon is air. And when all the components are moving at the same speed, so when the group velocity is equal to the phase velocity, then the different components of the wave are not overtaking each other, and so we have no distortion. And instead, when we have that some components of the wave are moving at different speed, we can perceive a distortion. This is true for acoustic waves as well, because sometimes high frequency or low frequency can have a slightly different propagation speed, and a sound that is generated far away from us can reach us, our ear or our detector, and it can appear to be distorted. So it's not exactly as it was produced. That's because the different components of the wave, different frequency of the wave, are traveling at a slightly different speed. So when we reconstruct the wave or the sound farther away from the source, we can find out that actually air is not can be a slightly dispersive medium. An example of non-dispersive medium is vacuum for the waves that are using vacuum as a medium. Sometimes it's a contradiction, it seems, in classical physics, that we have a medium that can transport energy and momentum, which is the vacuum. But actually, what is oscillating in vacuum is not matter. They are not particles. They are not gases. But is the electric and magnetic field that you just had a brief overview with Atzeni in MHD equation and so on. So what is propagating in vacuum is LD, electromagnetic wave, which we call light. And the vacuum for light is a non-dispersive medium. It means that when light is propagating in vacuum, all the components are traveling at the same speed, which is the speed of light. This is not true anymore when we are propagating, for instance, light inside the plasma. And this is one of the main topics of our lecture in the next few meetings that we're going to have, so in the next lectures. So we started with an example where our omega K dispersion relation is describing a non-dispersive medium. Let's now move on to an example where actually we see that there's a dispersion, and this is an anticipation of what we are going to find for waves in the plasma. So let's change and make this example of a dispersive medium. And then we have a dispersion relation. So we'll see later on, e.g. a plasma. And an electrostatic wave or electromagnetic wave in a plasma. Our dispersion relation is omega squared equals omega squared p, which is going to be the plasma frequency, for instance, in the plasma, plus v squared k squared. So as you see, this is a dispersion relation written as a function of the square of both omega and k. This is a constant term, which we see is the plasma frequency. And with respect to what we've had before, when we had only this term, we are summing up a constant term to the dispersion relation. So let's represent this in a plot. Same again. And this is important that you learn how to do it, because usually at the examination, we ask for representing a dispersion relation. So we represent omega as a function of k. As you'll see, a dispersion relation lives in positive values of omega. So we don't have the negative part for the angular frequency, but we can have both positive k vectors of wave numbers, sorry, and negative wave numbers, representing progressive waves and regressive wave with respect to the spatial direction x. So we want to represent this function here, which obviously, if you translate this into a function of omega as a function of k, is just the square root of omega squared, omega plasma squared plus b squared k, and then we have a plus minus here in front. So we have two branches, the positive branch representing progressive waves and the negative branch representing regressive waves. So is symmetrical. It's symmetric with respect to the to k. And let's draw it with a color. We use blue, for instance, for the progressive part, and red for the regressive part. So we see that we have a minimum for omega. We see that for k equal 0, the angular frequency of the wave is just omega p. So we have a minimum here that we can draw on the axis. And then as k goes to infinity, this term drops, and we see that for let's write this just a study. Omega for k equals 0 is equal to omega p, and for omega for k that goes to infinity, it goes like plus minus v times k. Okay, I forgot a square here, k squared here. So we see that for very large k, the dispersion relation is approaching and approximating the non-dispersive relation that we had before. So representing a straight line. So we know that for very large k, the plot will go as a straight line, and this is the progressive part. Actually, that was blue, if I remember. Okay, this is the asymptotic behavior on one side, progressive part, and then we have the asymptotic behavior for the regressive part. And we know that here the limit is omega p. and this smoothly increases, and then it goes as plus vk, and the same is on the other side. Okay. And okay, let me write here. This value here is omega p as I showed it here. Okay. So let's, this is the dispersion relation. Okay. The non-dispersive relation, you remember, is represented at these two lines, two straight lines, where the phase velocity and the group velocity are the same. So it means that the slope of the dispersion relation is not changing in time, in space, sorry, in k-space. Here instead you see that the slope, which is d omega over dk, which is the group velocity, is changing. And here we have that the slope is zero, and where the slope is zero, it means that the group velocity is zero. And then the group velocity is increasing, the slope is increasing, and then asymptotically, for large k, we see that the group velocity is again equal to the phase velocity. Let's compute the phase velocity explicitly and the group velocity. But before that, let me set the timer again, so not to overshoot. Okay, we'll have a break at 10. And okay, we have to compute the phase velocity, v phase, which is defined as the ratio of omega and k. So we, omega is the square root of this function here. So this is square root of omega square p plus b square k square divided k. So we can write it as a function of k. We take out one v here, once the speed of the wave, and then we have that what it remains is 1 plus omega p divided v times k square, and then the square root of it. So we factor out the original speed of the wave, v, which is called the characteristic speed of the wave now. And we see that when the k goes to infinity, this term goes to 0, and the phase velocity approaches b. When on the opposite side we move in k from a given number towards 0, so for k going to 0, this denominator goes to 0, so the argument of the square root goes to infinity, and the speed, the phase speed goes to infinity. Let's compute the group velocity as well. The group is d omega over dk. If you take this function here and compute the derivative with respect to k, you find out that here again you can single out a v, and then we have k in front on top, and then we have the 2 at the denominator, we have k plus omega p divided v square, and then we divide the argument. So derivative of k squared is 2k, so we can cancel out the factor 2. And we found out that the group velocity has a different, is not equal to the phase velocity anymore. Let's see what these two functions are leading to. So the two asymptotic values. We have that, for instance, for k much larger than 1, so for k going to infinity, which corresponds to a very short wavelength. So remember, when the when the wave number goes to infinity, the wavelength of the wave is going to 0. So lambda much less than 1. Then we have the velocity of the phase. Phase velocity is approaching v, and the group velocity is approaching v again. So for very large k or very short wavelength, the plasma is becoming non-dispersive. So the group velocity and the phase velocity are the same. Instead, if we go towards 0 wave numbers, it means very long wavelengths. Then we see that the phase velocity goes to infinity, and on the opposite, we see that this derivative is for k going to 0 is going to 0. So the group velocity is going to 0. What does it mean that we can interpret this situation telling that the phase velocity is going to infinity, but it's not a physical velocity, is a mathematical artifact of the Fourier transform. What is important is that the group velocity goes to 0. So the quantities transported by the wave are not moving at large speed, at the speed of the phase, but they actually start propagating inside the medium. So which when the group velocity goes to 0, it means that the wave is non-propagating anymore, is a non-traveling wave. So a non-traveling wave becomes an oscillation. It's something that might oscillate locally in time, but it's not moving while oscillating. Whereas if you remember, a wave phenomenon is an oscillation in space connected with an oscillation in time. So we have, for instance, the wave motion of the acoustic waves, or the waves of the sea, so hydrodynamic waves. So in this case, we say that the wave is non-traveling. And let's see again in a dispersion relation plot where this is happening. So suppose we have a general dispersion relation, goes like this, for instance, a branch of a dispersion relation. And let's focus our attention on a given point here. This point is telling us that in order to the Fourier component to be a solution of the wave equation, for this given k, omega has to be this one here. Okay. At that point, what is the so this is the k value, and this is the omega value of the wave. So what is the phase velocity in this case? The phase velocity is, let's take this slope here. The phase velocity is represented by the ratio of omega over k. So it's just the slope of this line here. It's connected to the angle that this line starting from the origin and connecting the point in the on the dispersion relation is making with respect to the k axis. So this is the phase velocity. And what is the instead the group velocity? The group velocity is the slope. So in the given point. So this is d omega over dk, and this is the group velocity. So you see in this case that the slope of this point, the phase velocity, is larger than the group velocity, and the two are different, two different slopes. And when we move towards zero, we see that the slope of the phase velocity goes to infinity, as we found again, I found up here. And so let's go to zero. And instead, the slope of the group velocity, which is the tangent of the dispersion relation in omega k space, goes to zero. So for k equals zero, for wavelength going to infinity, these solutions are almost a stationary solution. So they are oscillation, they are not traveling inside the plasma or inside the medium. Okay. So this is the first part of our introduction to wave properties. We've seen the 1D equation, wave equation. We found the relation between the progressive and the regressive wave. We took the Fourier transform, and we introduced the concept of omega and k. So the angular frequency of the wave and the wave number k of the wave. And in order for an important point was that in this space, the points that are solution to the wave equation are described by a curve. A curve in omega k space, which is called the dispersion relation. And we studied the properties of the dispersion relation, in particular the phase velocity connected to the speed of propagation of the mathematical phase in a Fourier transform, and then the group velocity, which is the slope of the tangent curve to the dispersion relation that is giving us the speed at which physical quantities are traveling. This is a very important concept that we spend almost an hour on recalling and redigesting them, because they are very important now that we discover that we are going to describe the wave phenomenon in a medium which is the plasma, and we just anticipated that the plasma is a dispersive medium. So we'll have this kind of dispersion relation curves. And this kind of dispersion relation are rather interesting because we see that they're approaching for very large k, so for very small wavelength, a non-dispersive medium. But when we go to very long wavelengths or very small k numbers, then we see that the fact that the medium is dispersive is showing up, and the speed at which the wave is transporting energy, for instance, is progressively going from the characteristic speed at large k vectors, which is going to be the, let's say, the free speed of the wave, is approaching zero as we go to very small k vectors. And we'll see that, especially in this particular case, the tangent is zero, so the group velocity is zero, so the wave is non-traveling anymore. And this will describe an oscillation. All this because what we want to do is to recover what you started to learn with Professor Azzeni in the very early part of this course, which was the plasma oscillation. Plasma oscillation were occurring in the plasma at a frequency which is actually the plasma frequency. So this is actually our dispersal relation that will be able to describe not only propagation of electrostatic waves in a plasma, but in the limit of very small k numbers will describe the oscillation of plasma oscillation that you find at the beginning of the course. So you see that when k goes to zero, this term is disappearing, and what it remains is telling us that it's not propagating anymore, but locally the phenomenon is that of an oscillation at the angular frequency, which is actually the omega frequency, the plasma frequency, sorry. Okay, so this is going to be our objective in order to recover what you've seen before as a limiting case. Now, we've seen the 1D equation for waves, and we have to introduce some technicalities in dealing with waves. Waves are usually described as a perturbation to an equilibrium state. If you think about, for instance, of acoustic waves are, so sound waves are a perturbation of pressure and density. Perturbation of what? Perturbation around the equilibrium value, which is, for instance, here at the surface of the air, we have that the air pressure is 1 atmosphere. So around 10 to the 5 Pascal. This is the equilibrium pressure at the sea level, more or less. And acoustic waves are perturbation that we generate for with instruments that are changing locally the pressure of the air, and then a local perturbation around the 1 atmosphere value is a very small, actually, pressure value is what actually is called a perturbation. It's very small compared to 10 to the 5 Pascal. It's much less, it's 1,000 or 10 to the minus 4 of the reference equilibrium value. So most of the formalism of waves relies on this technique of taking an equilibrium state like air at 1 atmosphere, constant pressure, then produce a small localized perturbation in pressure, and observe this perturbation. What does this perturbation initiate? Initiate it a continuous interplay between a local increase in pressure will cause nearby an increase in density, so a local compression. This compression will itself induce a local pressure increase in the neighboring layers of air, and this will set up and link together evolution of pressure and density that eventually is what is happening in the wave, in acoustic wave phenomenon. So there are fluctuation, perturbation of pressure and density that are linked together, and where one is generating the other one. So acoustic wave are an important benchmark to understand what is the wave mechanism. And the same is true, for instance, in a spring. You study, for instance, in general physics too, maybe the wave they are propagating along a cord. When you pluck the cord, and then the propagation is traveling along the cord. And in that case, the phenomenon was very interesting because the wave was transverse to the direction of propagation, which was the cord itself, or the string. And what is missing? I think I've said everything that was to be said. And the idea is so to have a medium where which we want to describe, and the wave phenomenon is due to the combined oscillation of at least two physical quantities. For instance, for acoustic waves, as I told you, they are the pressure and the density, local density of the gas, of air, for instance. So we need at least two players that are exchanging in a dynamic way some kind of interaction. And for instance, for electromagnetic waves, for light waves, we have the two dynamical quantities that are oscillating are the electric field and the magnetic field. In the plasma, we see that, for instance, we can have the electric field and the electron population, so the electron density or the speed of the electron. And so we have to identify these dynamical components and see what kind of equation we can write in order to link them and solve them. Before looking for a wave solution, not all the quantities are a solution to a wave equation. But before that, we have to identify an equilibrium situation when that we perturb this equilibrium. So we work with what is called the perturbation theory for waves, and then we linearize. So this is what is called the linear theory. We take only the perturbation, the main contribution to the wave, and then we have to apply this what is called the complex notation. So in the next lecture, we'll see that the technique is to linearize the equation and then transform the equation in a complex notation that will change the differential operators into and the differential equation into algebraic equations. So we have that we can give a title to this part. It's called linear theory for the waves. So linear means that we are going to produce a small perturbation and take only the linear term. So, for instance, let's imagine to have a function or a quantity f, which can represent the density, the temperature, the pressure, the electric field, one component of the electric field, and so on. So this is going now to be a function of x, vector x, so it's a position in 3D space, and time. So remember that a wave differential operator is mixing time derivatives with spatial derivatives. And by linear theory means that we express locally, for instance, this quantity, the F, that could be the pressure or the density, as a function of two terms. So as a sum of two terms, F naught, which is going to be the equilibrium value, plus a small perturbation, F1. So we'll see that the linear theory is linked to F1, which is a small perturbation. Somehow like expanding locally any function f in the constant term, which we call it the equilibrium term. And a small perturbation linear term that is arising due to a local perturbation to the quantity. And we'll impose the fact that actually the value of F1 of the perturbation has to be much smaller than the equilibrium value. So this is called linear theory or perturbation theory. Second ingredient is we express the perturbation using the Fourier transform notation. So for us, the perturbation will be F1. It's going to be an amplitude, F1, which is going to be, for instance, a complex term as well. So amplitude plus a phase times a k x. I introduced the scalar product between the k vector and x, and we'll see in a second that this is representing a plane wave minus omega t. So this term here is representing a plane wave. What is k vector? The k vector is the direction along which the wave is propagating. So for instance, let's take a direction like that and call it the k direction. And let's take some planes like that. No, didn't go well. Let me try. Okay. So these are plane of constant phase, we'll see. And we have many of these planes. Okay. Where the phase is constant, and the k vector is orthogonal to these planes. And so now we have that the k vector can be is carrying two important information. One, which is the distance between two equal phase plane, which is the wavelength, and it's called the wave number. And the other one is the direction, which is the direction in which the wave is propagating in 3D space. So what I represented here actually is in 3D space. So K is called the wave vector. Whose direction is the direction of propagation of the wave, and whose modulus of K, which we call it just K, is the wave number. And remember that the wave number k is equal to 2 pi over lambda. So if we take two of these planes here, the distance along the propagation direction k of the two planes is a wavelength, which is just 2 pi over k. So you see that by using the wave number and the plane wave solution, we have almost the same notation that we used before when we had kx minus omega t, but now we have the scalar product of the wave number and the position. So this is telling us that actually if we move along the direction of the wave, we have a 1D problem, which is so that in the transverse direction has the same properties. So that's why this solution here are called plane waves. In order to reconstruct the general wave in 3D space, then we are going to sum up on whatever plane waves for any given amplitude, any given k and omega pair, satisfying the dispersion relation, and for any direction in 3D space. So by using this function space, we can describe any wave propagating in 3D space. We can take a break right now. Let's just conclude this saying that we have a k vector. K is the direction of the wave. Modulus we have. The other quantity that we have defined before, but we have to recall, is omega. And omega is obviously the angular frequency. So omega is the angular frequency of the wave. If we want to express the frequency of the wave in hertz, then remember that just hertz is omega divided to 2 pi, and then you get the actual frequency of the wave, as we were doing with collision frequency before. Okay, let's take another 10 minutes break, and after that we start with the linear theory. Any questions? Okay, see you in 10 minutes time. Okay. Let's proceed with the linear theory. So we introduce the concept of small perturbation F1. I just repeat what I wrote before. F1, which is an amplitude represented by an amplitude times the expansion in plane waves. So is I k scalar x minus omega t. This is in complex notation. What we want to do usually, as we do with the complex notation, is we move on to the complex notation, and then we remember that actually this wave phenomenon is representing a real phenomenon. So we'll take the real part of the equation and drop in the pure complex imaginary part. And this can be done because all the operators, differential operators, are linear. So we can move or promote, let's say, a real phenomenon into the complex space where we can deal with phases in very easy way, and then go back on to the original real actual space by dropping the imaginary part. So it means that when we write this into plane wave, we mean that in the end our perturbation is going to be okay. We can write this as a cosinus of kx minus omega t plus I sinus of k dot x minus omega t. Okay, so we have a real part and the imaginary part, and in the end we can just drop the imaginary part and take only the real part of the solution. Okay, so what we want to do is we have expanded our general solution on general perturbation in plane waves, and we want to apply differential operators. So we move from the differential operators onto the complex notation. So we using the complex notation, so representing quantity as a complex number in and exponential of this complex number notation, will allow us to change differential operators or differential equations into algebraic equation. So let's see what this means. So suppose you want to compute the d over dx of our f1. So we have f1, and we take the derivative with respect, the partial derivative with respect to x of the exponential factor, which is representing actually a plane wave in 3D space. And this is, okay, this is not I, it's just 1. And 1 means for first order perturbation. And so we have an amplitude, and then, by differentiating, taking the derivative of the exponential, we find the exponential again, times the derivative of the argument, kx minus omega t, times, we have that this is actually represented, and we write it for the first and last time, This means kx times x plus ky times y plus kz, the three components of the wave number times the three components of the position x. And when you take the derivative with respect to x, all the other terms like y, z, and t are not depending on x. So the only thing that depends on the actual coordinate x with respect to which we are now taking the derivative. It means that what it survives is that we drop one kx factor. So we see that we can express this as f1 times the exponential is the original perturbation. So it's actually f1. And ikx is the factor that drops when you take the derivative of the perturbation. So we can see that we can substitute the differential operator derivative with respect to x, which in short notation is dx. We can substitute for multiplication by a factor, or which is the imaginary unit I, kx. And yes? Are there any questions? No? Okay. Same is true for instance, dy is becoming a multiplication of our perturbation of I times ky. dz becomes I kz, a z component of the wave number. And if we do the same trick with time derivative, so d over dt is becoming, you see that when we derive with respect to time, we drop a factor which is minus I omega. So the derivative with respect to time is equal to multiplying our perturbation by the factor minus I omega. And if we combine the three special derivatives into the vector notation, you know that you have the nabla operator, which is the basically the gradient operator we apply to a scalar function is equal to dx, dy, dz. The nabla operator is becoming equal to multiplying times I and the k vector, so the wave vector. So you see that whenever we find a derivative with respect to time or with respect to space, we can substitute using the complex notation the derivative with a multiplication times a factor that for special derivatives is proportional to the k vector component along the given direction, and for time is minus I omega, so the angular frequency. Then, in order to conclude this topic, we have to stress out the fact that we are using the linear theory, and linear means that we are going to retain only terms which are of the first order in the perturbation on the expansion or product of quantities. So the perturbation theory means that we retain only first order terms. In the perturbation. So what we do here, for instance, we have two quantities, could be the product, for instance, of the density and of the pressure. So for instance, we have two general quantities like F that we described before. So it's F0, an equilibrium value could be if F is the density, for instance, the background density plus a perturbation to the density. And then maybe another quantity that we call G, which is going to have, for instance, its own equilibrium value times the perturbation. So as I told you, this could represent density. So this is the perturbation on the density, and this could be pressure. So G1 is going to be the perturbation on the atmospheric pressure for acoustic wave. So when whenever we have the product of the two, what we're going to see? We're going to see that when we have, for instance, F times G, we want to evaluate this product. So we have four terms, F0, G0 times plus F1, G0 plus F0, G1 plus F1, G1. Okay, and now we see that in this product of the two quantities, we have an equilibrium product. This is the equilibrium value of the product. Then we have the two terms, which are the linear terms. So they are first order terms in the perturbation. What does it mean, perturbation? Let's remember that perturbation means that F1 is much less than F0, the value of F1, and the same is true for G1, is a perturbation with respect to the equilibrium value of G0. So this is whatever it is an equilibrium value. It might be large, it doesn't matter, but we see that this term here is of second order in the expansion. So if F1 and G1 are much smaller than F0 and G0, it means that this term can be neglected. So we'll have that second order terms are not retained. Second order are neglected. And by doing this, we'll see that in the wave equation, when we combine different quantities like pressure and density, for instance, we have again an equilibrium value for the product. Then we have two contributions that are mixing the perturbation of one quantity with the equilibrium value of the other one, and vice versa. And these are the terms that are actually giving rise to the wave phenomenon, the terms that we are going to retain. So this is, in the end, what is called the linear theory. We expand any quantity of interest into an equilibrium value and a small perturbation with respect to this one here, and we let the quantity interact together with the dynamical equation that can mix them. And in the evaluation of the equation, we are going to retain only the linear part. Okay, and this is enough to actually pinpoint what is the wave phenomenon. Remember that a wave can be thought as a a phenomenon that happens over an equilibrium situation. As I told you, we have an equilibrium state of air at standard pressure, 1 atmosphere, and the acoustic wave are a modulation, perturbation of pressure. And when you pluck a cord or a string, you have the initial tension of the string that gives you, let's say, the note of the vibration. Then you pluck it, and then you have the vibration of the tension state of the string with respect to the tension that you set up by tuning the string. And this perturbation is transferred to the neighboring layers of air that are close to the string. And so you initiate a perturbation in acoustic, in pressure, that gives a rise to the acoustic wave that you hear. When you pluck the cord, then you hear the sound. Okay. That's the mechanism. We want to have to focus and very clearly in front of us. So now we have all the tools and we are ready to deal with waves in plasma. So the next topic is actually using all this notation in the context of plasma dynamics. So really we enter the topic of waves in plasma. Let's put a timer. So we'll 20 minutes more. So we stop at 10 to 11 something. And we've seen the dispersion relation and the property of the waves. And now we want to see how we can get to a dispersion relation for waves in a plasma. So we concentrate at the beginning on the notation of the wave. Now we want to understand what are the phenomena that are leading to a wave propagation in the plasma. So we need the dynamical quantities that are going to evolve as a wave, and we need a dynamical equation that are connecting together these different quantities. I anticipate that with respect to a gas, we have where we have density and pressure that gives rise to acoustic wave. In a plasma, we have, as you might know by now, we have two new players that are interacting with the gas properties of the plasma, and these are the electric and magnetic field. So actually, we have that the plasma combines the gaseous interpretation of acoustic wave, where we have particles that are interacting with each other by means of pressure. And so we have, a plasma can sustain acoustic waves as well. But then we have that the elements that are composing the plasma are mainly two species, as you know, the electrons and the ions. And these electrons and ions are talking to each other, not directly, by they are interacting with each other by means of exchanging electrostatic forces of repulsion and attraction, or by means of current. They are generating current, and the current are generating magnetic field, which in turn is deflecting the currents and the trajectory of the particles. So actually we have two more players, which are the electric field and the magnetic field. So the plasma is a really what is called a benchmark for wave solution and wave equation, because we can build up or construct waves that are originated from the interplay of the electron species on the ion species with electric field, with magnetic field, and exchange every time the players, we generate different waves in the plasma. We see that we have the acoustic waves, but we are going to see that we have electrostatic waves where only the electrons are taking part, and we have ion electrostatic wave where only the ion is taking part and the electric field. Then we are going to have electromagnetic waves where the electric field and magnetic fields are playing together, and mainly they are interacting with the electron species because they are the most ready to respond to a very high signal frequency as the light propagation. And then after all this, we'll see a case where we have a magnetohydrodynamic wave. It's called the Alfvén waves, which is combining or linking together the speed, the average speed, so the bulk speed of the fluid, of the magnetized fluid, and the magnetic field itself. So we see that we find inside the plasma many different ways of producing waves. Just bear with me for the tongue twister. Okay, so we need dynamical equations. Okay, and players. So in a plasma, we start with one equation that you've seen, which is the Faraday's law. So curl of V is going to be our first equation. Curl of V is minus the time derivative of B. Okay, and this is called Faraday's law. Okay, another dynamical equation for the electromagnetic field is Maxwell-Ampere's law. So curl of B is equal to mu naught times J, the current density J, plus we have mu naught epsilon naught, the time derivative of the electric field, which is called the Maxwell Ampere's law plus Ampere. So we have Ampere's law, and we add to it the displacement current due to Maxwell, as you might remember. So we are going to allow our equation to describe very high frequency phenomena, which will lead eventually to the onset of electromagnetic waves in the plasma. Okay, these two equations are coupled together, and you see that here we have the electric field and here the magnetic field, so the two are directly speaking to each other in the Faraday's law. So there's no medium here connecting them. They are just the electric field and the magnetic field. Instead, in the Maxwell-Ampere's law, we see that the magnetic field B is linked to the current density, and the current density is a property of the medium, of the plasma. So the equation that links the electromagnetic field with the plasma properties, so the dynamic of the electron and the ions, is the definition of the current density J. And we can use them to close this set of equations, because we need to close this set of equations because curl of V is determined by B. Curl of B is determined by E and J as well. So we need something that links J to the other two players in our system of equation. And we use the microscopic Ohm's law. So we say that J is equal sigma, the electric conductivity, times E, the electric field in the plasma. And this is our equation that allows us to close the system of equation. Microscopic Ohm's law. Well, you might remember sigma is equal of 1 over eta, and eta is the resistivity of the plasma. And in general, sigma can be very complex, can be a tensor quantity if the conductivity is different in different direction, which is the case when we have, if you remember, a magnetic, externally applied magnetic field. So when we have a magnetized plasma, if you remember, we have that the magnetic field introduces as an anisotropy in space, determining, for instance, that the transport coefficient are quite different along the direction of the B lines, and with respect to for instance, thermal conduction or transport of particles, diffusion across the B field lines. So the conductivity and the resistivity J in general are can be a tensor, and can depend on the frequency of the wave, can have a dependence on the omega of the wave, and this is the only thing we are going to retain at the present. So for us, sigma is going to be just a scalar quantity, so it means that we are dealing with a non-magnetized so we concentrate our treatment here in a non-magnetized plasma. So there's no externally applied magnetic field, and this simplifies obviously a lot the notation. A sigma can be a complex function as well. So having inside it not only the oscillation of the wave, but the absorption of the wave, and we'll see this when we are going to deal with the attenuation of electromagnetic waves in a plasma. So this is in general our set of equations, and we'll try to combine them using the linear theory approach. So we have the dynamical quantities. So in this case are the electric field, the magnetic field, and the current density J, these three. And we have three equations linking them together. The technique is to linearize this set of equations, so expanding each quantity, like the electric field, the magnetic field, and the current density with respect to an equilibrium state, and then use the complex notation to transform this differential equation into algebraic equation, and then do the maths in order to get to finally to dispersion relation for these waves. So this is, as you see here, this is what we are going to obtain is a rather general form of dispersion relation, because here we just plug what? The fact that in a plasma we have an electric field and a magnetic field, they have to satisfy to Maxwell equation, and then we link them together with the presence of currents inside the plasma. Okay, so what we are going to obtain is a general dispersion relation for waves in the plasma that will be able to describe many different ways. So let's start our procedure by expressing this Faraday equation, linearizing them, and retaining only first order terms. So for instance, let's work a bit with Faraday's equation. So curl of E, and a very common technique is go here and look at this equation. We have the curl of E as a function of B, and curl of B as again a function of J and E. And the technique for obtaining a wave equation is to take the curl of both of them and combining them. The result is that one to increase one order or spatial derivative here, and we get to the D'Alembertian, to a second order differential operator, which is going to combine the second derivative with respect to space with the second derivative with respect to time, which is actually leading us to the wave equation. So let's take, so the general idea is to take the curl of a curl quantity. So let's take the curl of the Faraday's equation, and remember that spatial derivatives and time derivatives can commute. We can exchange the order. So this is becoming the curl of minus time derivative of P, and this we can exchange the time derivative, and this is becoming minus the time derivative of P, curl of P. Okay. And now we can plug in the curl of B, the second equation. So somehow we substitute for B, and we in this case we eliminate B, and we retain only terms that we will have the electric field and the current density J. So we have minus time derivative dt, and we plug the mu naught J, the Ampere's law, and then we can write, I put in a different color, mu naught epsilon naught, time derivative of the electric field, sorry. And pay attention to the notation that I'm using the vectors, because here we are working actually in 3D space for the dynamical quantities, the electric field, magnetic field, and the current density J. I highlighted mu naught epsilon naught here in order to remember that this is actually the definition of 1 over c squared, and c squared is a very important physical constant, is the speed of light in vacuum. So we'll see that actually this will lead us to in vacuum to waves that are propagating in vacuum without any dispersion at the speed of light. So we'll recover in the end the propagation of light in vacuum as a wave phenomenon. Okay, so move on, and we have that we can take the time derivative minus the, let's put it like this, 1 over c squared, second derivative with respect to time of the electric field. So, and this is the time derivative of the second term. And then we have minus mu naught time derivative of J. And we substitute for J using the microscopic Ohm's law. So now we have an equation which is a function of the electric field only. So we can plug sigma E inside here. Okay. So let's arrange these terms. So we have minus 1 over c squared, second derivative with respect to time of the electric field, minus mu naught sigma, let's leave it inside the time derivative, dt of sigma E. Okay, now is the right moment to use the vector, the complex notation. So what we want to have is to exchange differential operators for multiplications. And so we have, we go now to complex notation. Let's remember, what does this mean? We have an equation here, which is expressed for the actual dynamical variables, which are the local electric field, the local magnetic field in the plasma, and the current density. Now we, using our set of equation, we end up with an equation that involves only the electric field. You can see it here on the left-hand side and on the right-hand side of our equation. At this stage now, we want to move on to the complex notation. So we, the reasoning is behind this is that we expand whatever electric field is into plane waves in 3D space, and we use the superposition principle, so we concentrate our attention on a single component, so on a single plane waves, and then we obtain the dispersion relation that for a given plane wave will tell us which is the relation between the omega angular frequency and the k, the wave number of that plane wave. So let's go to complex notation, and it means, I'll write it here, that our electric field is going to be expanded around a given equilibrium solution that we assume to be zero, for instance, because in a plasma usually there's no externally applied magnetic field, so locally the plasma neutralizes the magnetic field, so the electric field, macroscopic electric field inside the plasma is zero. And then we have a perturbation E1 times E, the exponential factor kx minus omega t. And by writing this, I mean that then this can be a complex quantity. It's basically the Fourier transform amplitude of the electric field, although I'm not writing it, okay? It should be a complex amplitude. And this is just one of the possible plane ways in which I can expand the electric field. Okay, if I do this, then I translate, for instance, the Nabla operator I told you before, and we've seen that is becoming multiplication by ik. So we see that we have ik, and the curl is becoming the vector product. Okay, vector product, we do the same for the second one, ik, and then vector product of E, and we retain only the first order term. So we have that in one go we can linearize and go to the complex notation. And then this is the first, the left hand side. And now let's convert the right hand side of the equation. And then we take, actually we stop here and we update ourselves to next Friday. So we have here minus 1 over c squared. And then we have the second derivative with respect to time. The first derivative is equivalent to multiplying what? E1, the perturbation. I put everything that's new in red, so you know what is the single step from one equation to the other one. And then we have here that one derivative with respect to time, it means multiply by minus I omega. So I multiply twice by this factor, and I get minus omega squared. So I get minus omega squared, which is actually the second time derivative. And last term is minus mu naught, and the time derivative with respect to, sorry, the derivative with respect to time is just means multiply by only once minus I omega, the quantity that we want. So we have sigma and epsilon E1, which is the perturbation of the electric field. Okay, so this is our starting point, and by manipulating this equation, we are going to find the dispersion relation for waves in plasma. If there are any questions, you can ask them now, or we can update ourselves to next Friday at 8:15. We start lecture at 8:15 as today. Is that okay? Okay, I'll leave you think about and digest this part, that this notation that we've seen before, and we're going to apply it on next Friday. Take good care and see you on next Friday at 8:15.
Arrivederci.
Arrivederci.